pleasure to introduce Emily Griffith. She's an NSF Astronomy and Astrophysics postdoctoral fellow at CU Boulder. She got her PhD in astrophysics in 2022 from Ohio State University. And she's heavily involved in the ITSS survey, and she works as a co-chair of COINS, the Committee for Inclusiveness in CITA. During her PhD and her postdoc, she's been working on galactic chemical evolution and trying to understand things about nucleosynthesis using the stars in the Milky Way and also other galaxies. And we're going to hear about that today. And I think her schedule still has some times for meeting during the afternoon and a bit tomorrow morning if you wanted to sign up. Thank you, Emily.
Thank you, Nish, for the introduction. I'm really happy to be here and to meet all of you. I've had some really wonderful conversations this morning. So I'm going to talk about stellar abundances, mostly in the Milky Way, a little bit in our local group, and their implications for nucleosynthesis. The work that I'm going to talk about is that work that I did in my PhD and during my postdoc. So I have a lot of wonderful collaborators, especially in Apogee and Blah, who have worked with me on this. So the big question that a lot of my work contributes to is, where does the material that surrounds us come from? And this is like a big Carl Sagan question, right, that we often talk about with kids or when you go visit schools. And the first step of that answer, right, is that we're made out of stuff that was made in the stars. So a lot of the elements on the periodic table are made over the course of stellar evolution. Massive stars are fusing these heavy elements in their core, depending upon how massive they make it to different stages of fusion. This stuff comes out of the massive stars during core clock supernovae. They produce a bunch of elements on the periodic table, but mostly alpha particles like oxygen, magnesium, silicon, and some iron peak things like iron and nickel. The other heavier stuff, more of the iron peak material, is made in type 1a supernovae, or the explosion of white dwarfs through probably a couple different means. And together, these two processes produce a bunch of the material that we know and love. So here's a version of the periodic table where each element cell is color-coded by its astronomical source. So I'll mostly be talking about core cloud supernovae, exploding massive stars, which is shown in teal, and exploding white dwarfs, type 1a supernovae, which is shown in this light blue. And you can see that they make things from carbon down into this neutron capture peak area of copper, nickel, and other heavy things. These heavier elements on the periodic table are made through other extreme scenarios like merging neutron stars or AGB stars in the mass loss at the end of their lives. And I'll talk a little bit about that in the talk as well. But you can see that each element has a different combination of these processes. And this is our best guess at the fractional contribution to each of them. The iron peak, you see it's both teal and blue, and these alpha elements that are a little lighter are mostly dominated by core clock supernovae. We try to understand the formation of these elements as a function of time, and that's one of the big goals of the field that is galactic chemical evolution. So we try and describe the metallicity through star formation, and this stuff is coming from our core clock supernovae, type 1a supernovae, AGB star winds, merging neutron stars, and then all of this stuff is getting recycled back through many generations of star formation, coupled with inflows, outflows, dilution. All of these different star formation parameters are producing the abundance distributions that we observe in our Milky Way galaxy. So this is really a process that takes period over a long time. So we can complicate our periodic table even more and make each cell a graph. So here now, each cell, the x-axis is time, showing the fractional contribution as a function of time. And the one thing I want to stress here is just that we see our core clock supernovae enriched promptly. If we look at aluminum here, it's mostly yellow. And then at a certain time, we get contribution from other things like AGB stars or type 1a supernovae if we look at nickel and iron. So AGB and type 1a are delayed enrichers, and core clock supernovae is enriching promptly. And this is just our best guess at what this graph might look like. There's probably a lot on here that is very wrong, especially as we get into the heavy elements where we don't have a ton of observations astronomically of them. So how do we make this better? How do we improve our understanding? We have a pretty big toolbox for galactic chemical evolution. On the theoretical side, we have things like stellar yields, which are modeling stars over the course of their lifetime and their death. We have chemical evolution models, which are making like one zone toys of different regions of the galaxy. And then the extreme of that, galactic simulations, which are have all the dynamics and complicated star particles in them. Observationally, we have tons of abundances from spectroscopic surveys like GALA and Apogee. We have stellar ages that we can infer from many different methods. And we also have kinematics from Gaia. So we have a lot of information on the observational side and a ton of information on the theoretical side that we're trying to like mush together into one cohesive model of our Milky Way. I'll mostly talk just about three of these pieces: stellar yields, stellar abundances, and our chemical evolution models. But there's a lot more that we can add to this picture. So one of the big goals of galactic chemical evolution on the theoretical side is to reproduce the observed abundance distributions. So if we think about our one zone models, these are using yields from core cloud supernovae, type 1a supernovae, and setting parameters like the inflow rate, the dilution, the delay time of type 1a supernovae, and producing these tracks in abundant space. So here I'm showing oxygen on iron versus iron on hydrogen, or metallicity parameter, for some observed stars in gray, and then different chemical evolution tracks are those colored lines. And in each panel, a different parameter of the GCE models is changing. So we have star formation efficiency on the left, outflows in the middle, and IMF on the right. And you can see that each of these parameters change the shape of those one zone models in a unique way, but it might be a little degenerate with each other, right? Some of them can shift things in similar ways as well. So these GCE models have tons of free parameters in them, and we can break them down into roughly two categories. We have galactic scale things that are happening to the galaxy, like inflows, outflows, the total metallicity, the recycling rate. And then we have yield parameters, so the initial mass function and the actual amount of magnesium, iron, oxygen that's coming out of our core cloud supernovae, type 1a supernovae, AGB stars, whatever is getting mixed into this model. And it can be hard to tell these things apart. So this is one example of a couple of chemical evolution models compared to a bunch of elements that are observed through some different surveys. So those are the different colored points in the background. And there's two different GCE models here. The orange line has yields from core cloud supernovae that include rotation, and the green line does not include rotation. So this is just one parameter in the GCE model that is being changed here. And you can see that there's huge changes in some of these elements, like nitrogen and potassium. And some of those theoretical lines that are orange match the observations really well. Some of them that are green match the observations really well. And in some panels, neither of them are matching observations, right? So it's not clear just from looking at this picture that the chemical evolution model is globally succeeding at explaining the abundances we observe in the Milky Way. And it's hard to say what parameter you could change to fix this. Yeah.
So if you go back to one slide, are you thinking of the galaxy as just single blocks, or are you actually taking into account gradients?
So this is just taking in a single box. This is like the simplest version. You can also do multi-zone versions of GC where you like divide the galaxy in rings.
Do you need to do the multi-zone? Would it make a big difference to the results?
It does make some differences. These are really simple models, so we're just seeing like the singular track. And I'll show some denser observations in a couple slides, but the Milky Way's abundance distribution is bimodal in this space, so we have a high alpha population and a low alpha population. And so one zone models can't reproduce that.
Right.
So we need like multi-zone and dilution things. So
then you also need to account for stellar migration.
Yeah, radial migration, yeah. So there's many pieces of this. And the one zone models are like the simplest version of these chemical evolution models. They have many things that are wrong, but they're the easiest toy with the fewest parameters in them. So fundamentally, they're not going to succeed in reproducing what we observe in the Milky Way. Yeah, we don't want them to succeed. But the yields that underlie one zone models also underlie these multi-zone models of radial migration. So if these yields are not producing the right amount of potassium or magnesium, no matter if we include radial migration or dilution or anything more complicated, we're not going to get the observed abundance distributions. So it's hard. My main point here is just that galactic chemical evolution models are really hard to get to match the observations because there's so many tunable parameters that we don't know well enough that you can have multiple different versions of them that match your observed abundance distributions or completely fail in different ways. So it would be great if we could separate out these two types of parameters, the galactic scale star formation parameters and the yields, because in GCE they're really mixed together. One way we might be able to do that is leverage different abundance spaces. So oftentimes we look at abundances relative to iron, and iron is really sensitive to these galaxy scale things. It's coming from both quark cloud supernovae and type 1a supernovae. So it's sensitive to like the delay time distribution, the inflow rate, the outflow rate. But if we look at abundances relative to magnesium, so this is just some fake element, it's less sensitive to those variations in outflow or star formation variations. There's some differences. You can tell there's small differences in these tracks that are changing the GCE parameters. But it seems like it should reduce the impact of that. Okay, so how can we try and compare these theoretical models and our observations to best constrain the nucleosynthesis and the yields from these different sources? I'm going to talk about abundances from two surveys, mostly from Apogee, but also a little bit from Galah. Galah is a spectroscopic survey based out of Australia, so I like to show this with the kangaroos in front of the telescope. Galah is southern hemisphere optical, so solar neighborhood, not too much of the disk. Apogee is infrared, northern hemisphere and southern hemisphere. Great coverage of the galactic plane extending from solar neighborhood to halo to the bulge and bar region. Each survey has a slightly different mix of elements that they're able to observe based on their wavelength ranges. Notably, Galah has a lot more neutron capture elements, so those things that are named in neutron star mergers or AGB stars, whereas Apogee has cerium and C+, which can be a good age indicator. I like to show this just to stress the amazing things that SDSS is going to do in the next few years. So this is a plot of the stellar distribution that's been observed as of the last data release, 2 data releases ago, so DR16. And this is the Galactic Genesis program, which is underway right now and will finish in, I think, 3 years or so. So we're increasing the number of stars that are observed by an order of magnitude. We'll have high resolution spectrum for these stars, 10 to 15 elements for each of them, along with a lot of orbital information. And you can see that the coverage of the inner galaxy especially dramatically increases, and we'll get stars on the far side of the far and bulge region as well. So really excited for the future with these surveys. Okay, so this is the plot that I was referencing a little beforehand. In the Milky Way, we see these abundance distributions that are bimodal. So we have a high alpha population and a low alpha population. And the density of stars in each of these populations changes as a function of galactic position. So we have radius increasing here to the right and height above the plane increasing as you go from bottom to top. And you can see how this distribution is changing as a function of radius and height. If I just blow up one cell here, which is kind of close to the solar neighborhood, we can see this high alpha population, which I'll call low 1A, and this low alpha population, which I'll call high 1A. So these stars are often called high and low alpha because they have high or low alpha abundances. But physically, they're not enriched in alpha. They're just depleted in iron. They're not low in alpha, they just have a lot of iron from these type 1a supernovae that are enriching later. So the low 1A and high 1A is a reference to their nucleosynthetic origin of these two populations. We see that these distributions are changing across the galaxy, and that clues us into the fact that there's some pieces of a star formation history that's different in the outskirts of the galaxy versus the inner galaxy. We're producing different types of stars depending on their galactic location. While this is true and the density is changing, the position in abundance space of these populations remains the same. which is telling us that the underlying nucleosynthesis is pretty constant throughout the galaxy. So here the high 1A stars are in blue, the low 1A stars are in red. The population median trends of those two populations are shown as the lines, and the individual points are for the stars just in that specific radius and height cell. And you can see that in each of the panels, the black points lie on top of those colored curves pretty closely, within a few hundredths of a dex or so. And this is for manganese, which is an iron peak element, relative to magnesium. So again, magnesium here is a really powerful tool because it's only coming from core collapse supernovae. So when we look at abundances relative to iron of some element, we're seeing a mix of the core collapse and the type 1A contribution, since iron is made in both of those processes. But splitting things up and looking just with respect to magnesium really clues us into the origin of these elements just by looking visually at these diagrams. So as a toy of that, here are two elements, oxygen and nickel, relative to magnesium. We have the high 1A stars in blue and the low 1A stars in red. The high 1A stars have had a lot of enrichment from type 1A supernovae. So they should be rich in these iron peak elements like iron and nickel, but they should not have been enriched more in our alpha particles like oxygen, because our type 1A supernovae aren't producing more magnesium, oxygen, silicon. So when we look at these two populations in oxygen and magnesium, their median trends are right on top of each other because those high 1A stars don't have more oxygen from our type 1A. Conversely, the nickel, we see this really big gap because the nickel has been enriched by type 1A supernovae in this second population. So just by looking at these abundance distributions, we can say oxygen, it tracks magnesium well, it must be produced almost entirely in core collapse supernovae. Nickel, it doesn't track magnesium super well, so it must have additional contribution from another nucleosynthetic source. So this is the foundation of many models that try and predict abundances. Our abundances are actually very low dimensional. So while Apogee is measuring 10 or 15 abundances, we can predict them pretty well just from iron and magnesium. There's many different versions of these models, and I just worked on them as well, but they use alpha and iron, or age and radius, these two parameters, to predict the whole abundance space. So we can go from this high dimensional space down to a low dimension. And I have worked specifically with one of these models, the K process model. So this is extendable beyond 2, but I'm mostly going to talk about it in the 2 process version. The foundation of this model is that you can describe the abundances that we observe as the sum of nucleosynthetic components. So we have an amplitude and a process vector for each component, and we could add as many of these components together as we wanted. The simplest case is we have 2, a core collapse piece and a type 1A piece. The core collapse piece is conditioned on magnesium, the type 1A piece is conditioned on iron. So these 2 parameters are fit to different pieces of our abundance distribution. These process vectors are fit as a function of metallicity to each element. So they're describing like the elemental trend, the metallicity dependence of nickel, say, across our galaxy. And the amplitudes are fit to each star. So each star has some contribution from core collapse supernovae, type 1A supernovae, coupled with these metallicity dependent parameters that will give you the abundance that we observe. There's some assumptions underlying this that are wrong in detail, but they get us close enough, and I'll talk a little bit about the failures of them a little further on. So this is this simplest case of just 2 processes. We have a core collapse component and a type 1A component. We fit our amplitudes to all of the stars. We fit our Qs, these process vectors, to all of the elements. We have to fix what we're assuming for these process vectors for magnesium and iron. This breaks the rotational degeneracies within the model and grounds it in something where we can interpret it in terms of nucleosynthesis. So here's an example just for iron. So for iron, we're fixing these process vectors, so they're not metallicity dependent. We have a fixed core collapse and a fixed type 1a vector for it. And we fit every star with an amplitude of these two processes. And you can see it does a pretty good job. So on the left is the observed distribution in apogee of iron on magnesium to magnesium on hydrogen. And on the right is what we would predict plus noise that's on the scale of what we see in apogee. And the abundance distributions look very similar. If you look in detail, you can see some differences in the density on the high 1A sequence, but they look pretty good. And we can extend this to all of the elements within apogee. So here on the right are the different process vectors. You can see for oxygen, which we looked at just visually before, it tracked magnesium really well. So we think it's probably a core collapse element, should have a really strong core collapse vector. And you can see this purple, which is the core collapse, sits at 1, and the orange, which is the type 1A, is pretty close to 0 with some bump at the higher metallicity end. And if we look down at manganese, which is this third row, it is an iron peak element, strong enrichment from type 1A supernovae, and very metallicity dependent, we think. So we see this strong orange line that's increasing as a function of metallicity, and a pretty low core collapse vector. You can compare the observed and the predicted, and you see some interesting differences in some of these panels, right? So for oxygen, observed, we have this weird like splash of stars up here that's not in the predicted. So that would be some type of systematic that's in our oxygen abundances that can't be reproduced by the model itself. So if there were temperature systematics, surface gravity systematics in the abundances, if these stars have incorrect oxygens, the model isn't going to be able to get the observed oxygen because it was observed incorrectly. I also like to point out the cerium here. So the cerium observed distribution is pretty high. It goes up to large cerium to magnesium values, and the predicted does not reach that same peak here. So cerium is a neutron capture element. It's made in AGB stars and maybe some in core collapse supernovae. So its production is not perfectly tracked by magnesium or iron. So it might have a third process that it would need to describe it well, whereas this 2-parameter model can't capture the enrichment origin of cerium. Yeah?
Sorry if this was mentioned at some point, Mg, the magnesium hydrogen ratio, what is that proxy for?
Magnesium to hydrogen, it's just the metallicity. Yeah, so normally we plot things in iron to hydrogen. That's the like default metallicity parameter that people use. But I use magnesium because visually you can see these two sequences and it kind of gives you a clue into the nucleosynthetic origin. But it's similar, just tracking overall metallicity in a way that is close to what iron does. Okay. So we can fit these stellar abundance distributions and get an amplitude each star, process vectors for all the elements that are included. And these we tie back to these nucleosynthetic processes. So we're describing the abundances as a sum of our core collapse and our type 1A. We can then pull out fractional contributions of each of these processes, right? If we're summing everything and that gives us the whole abundance, we can say 25% of this star's iron is coming from core collapse and 75% of it is coming from type 1A. So we could do that for every star or just as an average along these population trends. So this is the core collapse fraction at solar metallicity for our stars in apogee that we derive from this 2-process model shown as these solid dark purple points. So if you just look at those for a second, you can see that it kind of tracks what we've been talking about and just inferring from the plots. Our oxygen is really high, core collapse fraction. Our iron peak elements, chromium, manganese, cobalt, nickel, are lower, closer to like that 50-50 value. The iron is fixed here. It's something that we set in the model is this relative fraction of iron at solar metallicity. In the light purple, I'm showing theoretical models. So we have all these different theoretical yield sets for core collapse supernovae, type 1A supernovae, AGB stars, and we could sum up how much of those different processes are making nickel at solar metallicity, and then find a fraction of that that's coming from core collapse. there's many yield sets in the literature. So this ChemPy GCE program is using just 2 different versions of those yield sets. So one set of Cork labs type 1A AGB, second set of Cork labs type 1A AGB, which are these triangles just connected by a line to give us a very rough estimate of the parameter space that these yield sets can span. And you can see for some of them, the observations agreed really well with the theoretical values, like our oxygen is really close, our silicon, sulfur, those guys are in good agreement. I like to highlight that the iron peak elements, they broadly agree, right? The theory is saying they have large contribution from something not core collapse, and we're seeing also they have these low core collapse fractions. But this theory bar is huge, right? There's a large parameter space of good development that our manganese would agree with. So there's giant variations in the yields for these elements just from yield set to yield set. And sodium is the big outlier here, right? Theoretically, our points are saying sodium should be a pure core collapse element. And observationally, we're seeing that it has a large component from what we are modeling as type 1A supernovae. Sodium is not made in type 1A supernovae, but it is made in AGB stars. So if these models don't have enough sodium production in their AGB, or if the AGB yields are not including sodium for some reason, then that's causing this discrepancy. So even within this, though, we've pulled out these galactic scale components from GCE models. Like, we're not thinking about inflows or outflows or star formation efficiency. We're just thinking about yields and trying to compare what we can observationally infer to the theoretical yields. Even here, we see a lot of disagreements, right? And what does this mean? What does this mean? How can we pull out from this huge error bar what's going wrong with theory from our observational constraints?
So, how large is the errors in observations here?
How large is what?
How large is the errors for the observational data?
Oh, for the observational data. Yeah, that's a good question. I don't have a good answer because it depends on how we calibrate the model, right? So we're assuming some fractional contribution of iron from quark clock supernovae and type 1A supernovae. So this is setting like the foundation of the model. So 40% quark collapse, 60% type 1A at solar metal is the assumption here. And when we come back to this plot, we can see that iron here falls right at 40%. So if we change what that's fixed to, it's going to shift these purple points up and down, especially in this iron peak. It won't impact the alpha elements very much, but it will impact these iron peak elements. And I don't have a good answer as to how much is a reasonable range there, because we don't know for certainty what the fractional quark collapse type 1A yield is of iron at solar metal.
So it depends on the primary distribution.
Yeah. But we can pretty strongly say that like manganese has more type 1A contribution than iron, right? The relative differences are pretty strong here. But yeah, there's definitely some error bar on these points. To try and get a better handle on how we can compare these observational constraints to theory, though, we want to try and look at just an individual source. So not quark collapse type 1A AGB all mixed together, but just one source. So I'm going to use quark collapse supernovae as a starting point. So quark collapse supernovae, as we know, come from dying massive stars. At the end of every massive star's lifetime, it's given a choice. It can form a black hole, or it can explode as a quark collapse supernovae. This is a little bit of a making something a binary that's not really a binary, but it's good for this purpose. We know that stars produce different amounts of the elements based on their core structure, and that's intimately tied to the mass of these stars. So here's just a couple of cores of stars from different masses, 4.3 solar masses up to 6.3. And the different colors are different isotopes of elements in those stars' cores. And you can see in some of them that these bars, the sizes of these bars are different. Like this is magnesium 24 and carbon 12 up here. And the relative fraction changes based on the core mass. This is going to change how much stuff is made in the explosion and the yields of these different elements in the explosion. The amount of stuff that comes out matters and is tied closely to how many black holes are formed, right? If these massive stars are collapsing down to black holes, then they're going to trap that material in them, and it's not going to make it out into the ISM, into new stars that are born. So many quark clock supernovae yield models make really strong assumptions about the black hole formation in these models. The simplest is that they assume all stars explode. Probably wrong, we know that there are stellar mass black holes. Or that the most massive stars collapse. So everything above like 40 solar masses or so is forming a black hole. These models that do this, they're just bombing their stars to explode. They're not actually modeling the explosion to see if the stars are collapsing or exploding on their own. They have to force them to explode. If we do more physically motivated models of quark clock supernovae and let them decide their end state, we actually see this really complicated black hole landscape. So here we have progenitor mass on the x-axis, and these are just a couple of calibrations of a complex yield set scaled to different energies. So the colored bars are successful explosions, and the dark bars are black hole formation in these neutrino-driven explosion models. And you see that they look kind of like barcodes. There's regions that form black holes at really low progenitor masses, so around 15, around like the mid-20s, and then around like the 40s range, and then some successful explosions up to these highest masses. And this is really interesting, and it changes the yields that you would get out of these stars if you have black hole formation at lower solar progenitor masses and successful explosions at these high masses. So the goal here is that we can try and compare these quark clock supernovae yields to our empirical constraints on our integrated yields from the observations themselves. These complicated black hole landscapes, like I said, matter to the overall integrated yields because the yields are not simply dependent upon the progenitor masses. So some elements like oxygen, you can see the oxygen yield is increasing as a function of progenitor mass. The background colors show again where the stars are exploding, purple, and collapsing to black holes in orange. The oxygen yield increases up to about 40 solar masses, where in this set of models, the star fully loses its envelope and the oxygen yield more comes out in the wind and drops off in the explosion. The iron, conversely though, you can see is really looks random with mass, right? We have these really high peaks and then this lower overall yield. And these high peaks in iron are in the regions where the stars likely collapse to a black hole. So if black holes are forming here, this large iron yield is not coming out into the inner solar medium. But if these stars are capable of exploding, they have really dense cores and they're going to produce a ton of iron. So their explosions would produce a lot more iron in these yield sets. So this iron is really tied to the core structure of these massive stars at the end of their lives. We can calculate IMF integrated yields for these different yield sets with different black hole assumptions and compare those integrated yields for different black hole landscapes to what we observe empirically. So there's a lot going on here, but I'll try and explain it. On the y-axis, we're showing the difference between those theoretical models and our empirical calculations. So I showed that fractional quark collapse plot with the ChemPy yield sets. We're taking that fraction combined with solar abundances and deriving just a quark collapse yield for each element from our empirical study and comparing that to the IMF integrated yield for different yield sets. And the different yield sets here are just different explosion landscapes from that complex black hole landscape figure I'd shown before. So the least explosive are these orange points, and the most explosive are these dark blue large points. The purple point is a proxy for this naive black hole landscape where we say the least massive stars explode and the most massive stars collapse to black holes. And that's somewhere in between the complex black hole landscape and that fully exploding. So you can tell if a point is above this line at 0, the model, the theoretical model, is over-predicting the yield of that element relative to what we would say it should be at from our empirical calculations. And if it's below, the model is under-predicting it. If our yields were amazing and our observational constraints were amazing, we would love to just be able to see one of these sets right on the 0, 0 line, and it could constrain the black hole landscape empirically from these yields. In practice, there are errors on our observational values, and there are lots of uncertainties in just this single quark clock supernovae yield set itself. And the differences here are likely telling us most about the uncertainties in the yield sets. So one thing that we see is that the oxygen is over-predicted in every single landscape, regardless of how explosive it is. This is common across all quark clock supernovae yield sets. Oxygen and magnesium, because we're looking at these elements on magnesium here, they're both produced entirely in quark clock supernovae, so there's nowhere else that this stuff could be coming from. But quark clock supernovae yields systematically produce more oxygen than magnesium. They cannot reproduce the solar oxygen to magnesium ratio. And uncertainties in the solar abundances don't resolve this. So this might be telling us that there's something wrong with the underlying reaction rates that are producing magnesium and oxygen in the stars over the course of their evolution, or in the explosion. So our triple alpha and our C12 alpha gamma. We also see really high carbon and really high copper here. So these might be other indicators of reaction rates that are wrong. The copper yield specifically probes like free neutrons in these models that are needed to make carbon, are needed to make copper. And the carbon is, a lot of the carbon comes out in the winds of these stars, so it might indicate that there's something wrong with the wind prescription here. I go into detail a bit if you're interested in what these different discrepancies could be caused by. So carbon, yeah, titanium 22, which is a source of free neutrons. So ideally, we would be able to empirically constrain our black hole landscape by comparing our observations in our theoretical side. But in practice, what we can really do is communicate back with these modelers and try and improve our stellar yields, talk to the nucleophysicists who are doing these reaction rate calculations, and try and make some changes to bring these yield sets into better agreement with what we observe. So these two process model constraints from fitting the abundance distributions themselves can be really powerful tools for understanding the relative fraction of contribution from quark clocks in type 1a, but also in constraining these theoretical yield sets. Okay, I've talked a lot about quark clocks in type 1a, but reference that there are some failures in our assumptions, right? We know that there are AGB stars and other processes that are contributing. Right? This model cannot actually perfectly reproduce the observed abundances, and part of that is because it's oversimplifying and making some assumptions. I'm going to pivot to talking about Galah for a little bit. Here's my Galah parrot to show you. And this has got a lot of information on it, but my point here that I want to make is that when we look at the residuals of this two-process model in the Galah abundance space, we see correlations between these neutron capture elements. So Galah has copper, zinc, yttrium, and barium. And the residuals away from the two-parameter model for yttrium and barium specifically are really highly correlated. So if if a star has more yttrium than our model would predict, it also has more barium than our model would predict, which would suggest that our type 1a component calibrated to iron is not perfectly reproducing this AGB mixture. So rather than refer to these as a quark clocks and a type 1a component, they're really a prompt and a delayed component. Our iron is being produced on a delayed timescale by type 1a supernovae. So a piece of any other delayed process is going to be captured in this iron component. So part of the delayed AGB enrichment is being captured by this iron process, but it's not perfectly tracking iron, so it's not going to capture 100% of it. We can make a simplified 3-parameter model by adding an AGB component, but only allowing it to help yttrium and barium, which we know are made in AGB stars. So we're going to force this type 1a component to be 0 for yttrium and barium because they're not made in type 1a star, type 1a explosions. And we're going to turn on this AGB component only for barium and yttrium. We fit this model to the stars and we get an amplitude for the quark collapse, type 1a, and AGB process for every single star. And we see that the type 1a amplitude does not perfectly track this AGB amplitude. So there's some stars that need more of this AGB amplitude than type 1a. If the AGB process wasn't doing anything, it wasn't adding any information to this space, then we would see this follow the one-to-one line. But it's skewed up, suggesting that a bunch of these stars need additional enrichment from this AGB parameter that can't be captured by type 1a supernovae alone. Just kind of confirming what we saw in those residuals, that we do need an AGB process, a third process, to explain some of these neutron capture abundances. They can't be captured just by quark collapse and type 1a. It's really difficult, though, to detangle this in detail because we're not measuring many of these elements. GLA has other neutron capture elements, but they're not reliable. They're only really measure barium and yttrium well. In apogee, we only have cerium. We also have C plus N, carbon and nitrogen, which might be made in AGB stars. But the number of elements we can probe these other processes with are limited. And the deviations from a 2-parameter model are very small. So the quark collapse and type 1a component, even though it does a bad job of predicting barium and yttrium, it can do it close, like it can get within 1/10 of a dex or so. And at this scale, we're reaching the systematic noise on the abundances. So we have systematics that go with temperature and surface gravities that can be really hard to disentangle. So we're working on trying to make a more complete 3 or 4 process model, but it just is difficult to do with the abundance precision we have from these surveys. Okay. In the last little bit, I'm going to pivot to what I've been working on in the last year or so. And one question is, what about other galaxies? So everything I've shown you so far is done for the Milky Way disk. In the Milky Way disk, we have hundreds of thousands to millions of resolved stars that we have abundances for. And we don't have too many other populations that we have resolved stellar abundances. But we do have the local dwarf galaxy strains, and we're starting to get resolved stellar abundances in M31. If we just look at the magnesium on iron versus, iron on magnesium versus magnesium on hydrogen distributions of these different populations, we see that they're very different from the Milky Way. So we have LMC, Sagittarius, and M31, and none of them track this high alpha and low alpha sequence that we see. This is because they have had very different chemical evolution histories, right? They have different star formation efficiencies. The Milky Way has probably had mass inflows, whereas these dwarfs have not. And so those different changes change the shape of these distributions, the place where the abundances turn over, and their overall normalization. In Sagittarius, you can kind of see this tail down. So this is probably coming down to a quark collapse plateau, and then type 1a stars turn on and they produce more iron, and it kind of comes up along the scale. M31 is really interesting because in the Milky Way, we have this bimodal distribution in this parameter space. And the preliminary data from M31 show it as a single evolutionary sequence. So we're trying to understand, is the Milky Way unique? Are other galaxies like our own? And I won't talk about M31 beyond this, but I think it's really promising, and we're going to get a lot more data for it in the next 5 years or so. But LMC, Sagittarius, GSE, which isn't a dwarf, but we can select the GSE stars in our halo, which probably was an accreted structure that fell into the Milky Way and treat that as a different stellar population than the Milky Way. And we can try and understand if the abundances of these populations fit within our Milky Way model. So we can fit a 2-parameter model like the ones that I've discussed to the Milky Way disk, apply those fits to the dwarf galaxies. So those process vectors we're keeping constant, and we're just fitting those amplitudes to each of the stars. And then ask, does that model accurately predict the abundances that we see in these dwarf galaxies, or does it fail in some places that just turning up or down quark collapse and type 1a enrichment can't fully capture? It would need an actual change in these process vectors or the metallicity dependence to reproduce them. And we see that some elements are pretty well predicted by the Milky Way disk. So here's oxygen. This is the residual oxygen abundance. It's pretty close to 0. And other elements like C plus N are not well predicted by the Milky Way disk model. So the C plus N is systematically under-predicted in Sagittarius, GSE, and LMC. You can see that in some of the other elements like aluminum as well. And here's just a summary plot of these different residuals. So the average residual for each of these populations, Sagittarius in yellow, GSE in green, LMC in red. And so for sodium here, you can see that all of them are systematically under-predicted by a Milky Way model. And this is really interesting, right? This says that this model that we think is probing just these nucleosynthetic parameters can't capture the abundances in these local dwarf galaxies. The naive interpretation of this would be that maybe these type 1a quark clock supernovae are enriching differently in the dwarfs than in the Milky Way. This would be surprising that quark clock supernovae would work differently depending upon where they are, but that could cause these differences, right? Other reasons could be that, again, we're not including AGB stars in this model. So the 2 populations, Milky Way disk and dwarf galaxies, could have different amplitudes of an AGB process, which is not included here. Our abundances could depend on things other than magnesium. So our 2-parameter model is scaling everything to magnesium. You asked about why magnesium and hydrogen was on that x-axis. It's the metallicity parameter that we're using here. So if an abundance is made in quark clock supernovae and it depends on C plus N and not magnesium, we're not going to be able to perfectly predict its trend calibrating to magnesium alone. Or there could be pieces of our chemical evolution history that we're not taking account into this model that we are actually sensitive to. I'd shown at the beginning those fake GCE tracks in magnesium space, and they all looked like they fell on top of each other, right? So we think we're pretty insensitive to those galactic scale inflows, outflows, star formation efficiency in this space, but we're not perfectly insensitive to them. So there might be some remaining pieces of these galactic scale parameters that are influencing the nucleosynthetic model. One example could be dilution, right? The Milky Way galaxy has likely experienced a mass dilution event, maybe from the GSE merger, where a ton of hydrogen gas was dumped on the galaxy and it kind of reset our metallicity. These dwarfs are small and they probably have not had large dilution of hydrogen-rich gas. So things like that could change the abundances in a way that's not captured by this nucleosynthetic model. And it hints to the fact that the model might be sensitive to aspects of chemical evolution. So at small amplitude, can we see this in the Milky Way? Because we know that the Milky Way disk also has had different chemical evolution over its different orbits and spatial regions, right? At large amplitude, this model does a really good job at predicting the abundances. But if we look at the really small residuals, we do see interesting structure there. So this is just an example for sodium. Here is the overall distribution of the sodium residuals. So we're predicting sodium pretty well, like to about 0.1 dex in most of these stars or under, which is on the scale of the apogee error on the individual stellar abundances. We can measure the abundances to within the apogee error, or predict the abundances to within the apogee error. But when we average many of them in different bins, so here I'm showing the guiding radius versus the maximum height above the plane. So more orbital and action versions of these spatial parameters. We can see that the average residual is not random, right? So the darker colors, the darker blue is a more positive residual, and the pinker colors are a more negative residual. So we find that the mid-plane of the galaxy, on average, has a positive residual, and off-plane is more negative. And we can see this thin disk, the thick disk, this flare upwards, a flare of young stars in the outer galaxy that we know exists just like in the kinematic structure. So some of these residuals are tracing the underlying kinematic populations in the Milky Way. And this might tie back into what we see in the dwarfs, that these residuals are actually sensitive to underlying galactic scale parameters like inflows, outflows, star formation efficiency. And we're trying to tease out what this could be indicative of. Can we constrain any of those galactic scale properties with these abundances and these residuals? Oh, I have highlighted. Here's a thin disk, here's a flare. But I'll leave up my conclusions, and I just want to stress that these two-parameter models of nucleosynthesis can be really powerful tools in understanding our galaxy's chemical evolution, the nucleosynthesis, the underlying yields, and these other complicated aspects of star formation. Thank you.
Sorry, I may be mixed up, but I was intrigued when you showed the comparison of the abundances of the dwarfs, and that's how you were calling out that sodium was underpredicted. Wasn't sodium also underpredicted in an earlier slide? Or that there was a large discrepancy, I thought you would call that.
Oh. Here, the sodium, it's a little different. So here we're comparing the core class fraction between sodium and theoretical models. So this is saying that our yield sets are dominantly producing sodium in core cloud supernovae. But empirically, we would say that half of sodium is produced in core cloud supernovae and half of sodium is produced in some other delayed process, probably AGB stars. So that could tie in, right? We're not including AGB stars in this two-parameter model. So that maybe could help produce some of the sodium if we added that third component back in.
Thank you.
Yeah, you have mentioned stellar winds before, and I was also thinking about how like binarity would affect this. So yeah, could you elaborate a bit more?
Yeah, really good question. Binarity probably plays a huge impact, and only one yield set exists that has binary stars, and then I don't know if I have a slide. This doesn't show the binary stars, but our core clock supernovae grids are actually really limited. So the yield set that I showed is this top row. It has 200 different progenitor masses, which is huge. It's like a giant amount more than any other grid has. But it's only at solar metallicity, and it's only single stars. The yield sets that are typically adopted by folks when they do GCE models are like this Limongin-Chiaffi 2018 set, which has 9 progenitor masses compared to 200, but it has 4 metallicity ranges, 4 metallicity spaces. These push yields are another set that does neutrino-driven informed explosions rather than thermal bombing them. The Limongin-Chiaffi set assume low mass explode, high mass collapse to black holes. There's one set at solar metallicity that does a comparison of single stars and binary stars. They have explosions for them that have been thermal bombed, so you have to make assumptions about what's actually exploding or collapsing to a black hole. And I think their maximum solar mass is maybe in the 30s or 40s, and they have maybe 15 models, and only solar metallicity. And they just were published a couple years ago, so no chemical evolution model includes binary core cloud supernovae. And even then, that's one case of mass transfer that they were modeling. So in practice, our core collapse supernovae yield sets should be much more diverse than what we're actually including in theory. And this probably has huge impacts on the yields that are coming out because so many massive stars are in binaries, and many of them, a large fraction, are in close enough binaries that this mass transfer or stripping is happening. And this can really change, especially those light element yields, carbon, nitrogen, oxygen, magnesium. So I'm hoping in the next decade, we're gonna make some progress here. And I don't do this type of modeling, but whenever I talk to stellar modelers, I try and get them to do some more cases. But these are super computationally expensive and difficult calculations. So it'll take some time.
Well, not only these are very expensive, very complicated calculations, it's also very unreliable, I imagine. So is it possible to just go from, so I guess, you have a bunch of stars, each one have an abundance pattern. Is it possible to just go straight from the star and just do a linear algebra analysis and figure out the eigenvectors and so on? When you do that, do you get two eigenvectors?
Two can explain most of it, right? These two parameters can explain a lot.
Well, this is already has theory prior to that, right?
Only-
Like you're saying like magnesium is fixed and also iron is.
Yeah, that does have some prior. It's not connected to the yield sets, but we are making those assumptions
Right.
that
So
magnesium
if you
is
just
fixed.
I know nothing, database, can I get to orthogonal eigenvectors out of this somehow? People must have tried that soon.
It's a good question. I think when people do that type of decomposition, they get more than two. But they do see that like the alpha elements group together, the iron peak elements group together.
You mean it's not a clear decomposition?
Not clear, yeah. And you see like these neutron capture elements are a little different. And I think they find more like 5 to 10, 5 or 7 dimensions. They don't find 2, yeah.
But which you kind of expect, right? More metal-poor stars and have winds,
Right.
binarity can affect everything.
Right. Yeah, you can imagine, like the 2-parameter version of this model is very simple. You could have a component for 8 solar mass core collapse supernovae in the case whatever mass transfer, right?
Yeah,
And stack all of these processes into a very complicated thing.
that would be interesting.
Yeah, it would.
Assuming you get enough data now.
Yeah, we get enough data, but we have to really work on the systematics because when you get down to the hundredths of a dex abundance scale, it's really hard to see the true physics from the systematics or observational errors in the abundances. So having tons of stars helps with that though.
Thanks for the really interesting talk. I was curious when you showed the slide on residuals for the trends in residuals with location, if there are also trends with environment, or if that's something that you can begin to pull out, or if that's
Like what types of environment?
globular cluster versus
Oh,
field
yeah,
stars,
Yeah, globular clusters are not well fit by a Milky Way disk model, yeah, because they have really strange abundances that can't be tracked by just this core collapse and type 1a enrichment. So one thing we could try and do is fit the globular clusters with this model and see what changes in the process vectors or amplitude space it needs to explain them differently than the Milky Way disk, and maybe try and understand it from that direction. But I think that there could be some really powerful like abundance clustering analyses, right? Can you identify globular cluster stars just from their abundance residuals? Because they're going to be very different, and maybe highlight those abundance differences more than just doing clustering in a straight abundance space. But yeah, globular clusters are different. These dwarf galaxies are different. Halo stars are fit okay, but not great.
How important is it to have a very large sample for a method like this? I'm just imagining, obviously, like in a dwarf galaxy, you have a much less complicated picture. usually think of CRISPR sacrifice is sample size and the precision. Is that like a big thing, or could you say like sounds older, or kind of know what's going on, and it's a bit maybe easier to see in core labs, for example, at the lowest of the scan or something like that, to calibrate.
Yeah, it's a really good question. And so most of like what I'm doing here is using a newer version of this multi-parameter model that's more data driven. So the version that I used in my thesis, it's like scaling these values to median abundance trends in the population. It needed the bimodality to be able to fit a model. But we have a version now that doesn't need that. So we can fit it to like just the LMC or something, and we don't need a ton of stars. So thousands level, I think you could probably get a decent fit. I don't know how well you could see these types of residual trends, because here we're averaging like hundreds of stars in each of these little tiny radial and height bins, to try and get signals that are on the scale of the observed error, abundance error. So if you want to try and do statistical analyses on the residuals, I think it helps to have more stars, but you could fit the model to a pretty small population.
I think we can continue whatever questions are remaining, for example, my time and upstairs with this. Thank you, Emily, for this beautiful talk. Thank you for listening.